Hi, thank you for coming. My name is Marek, and I will be telling you about encoders, and specifically about encoders, neural encoders for natural language. That's because my work mostly involves work on natural language processing, but many of the ideas in this talk will be applicable to other tasks and types of data as well. Just to introduce myself, Jaak already introduced me a bit, but I have this nice slide as well. I'm a lecturer of machine learning at Imperial College London. I mostly work on machine learning and neural network models for natural language processing, and focusing on areas of like how we can design models that are better able to understand text and get the most information out of any textual data. And this involves a lot of work with neural network encoders, hence the talk I'm giving today. I'm also a visiting researcher at the University of Cambridge, and I'm a scientific advisor for Transformative AI, which is a medical technology startup that works on predicting cardiac arrest in critical care patients. And there we are actually working with ECG data, but applying a lot of the same ideas from natural language processing. We're also using encoders and neural network transformer models there. So this is one example of how ideas from NLP can be transferred over to very different fields. Previously, I was a postdoc at Cambridge, and I also worked as a researcher at SwiftKey, where I was researching neural network language models for predictive keyboards on text. In this talk, I'll tell you about encoders from several different angles. I'll start with a bit of background, some motivation, and I'll quickly go over some of the important early ways of encoding text. Then we'll focus on the state of the art, the modern neural network transformer models, and specifically looking at BERT. And finally, I'll be telling you a bit about some of the interesting experiments that my students have done using these models, whether investigating how they work internally or extending them with different interesting abilities. So first, a bit about the background. We want to have good models for language. We want to build different AI systems that are able to understand language and use it for many different tasks. But this is very difficult because language is so complex and highly compositional. It's really easy to come up with a sentence that nobody in the world has ever said before. Language is really complex, and this can be, does this work? It does. This can be illustrated by these two sentences here. So I bought a beautiful rose and I acquired a pretty flower. Imagine that our machine learning system sees the first one in our training data, but then comes across the second one during testing. We would want the model to behave the same way because these are essentially the same sentence with the same meaning. But if the model is just looking at the surface forms of the text, if it hasn't seen the words acquired or pretty before, then it won't know how to handle this sentence. So what we want to do is represent text as feature vectors in such a way that sentences or texts with similar meaning would have similar feature vectors. And we can then use those vectors as input to any kinds of machine learning models that then do a particular task on top. And a vector is just the sequence of values, and it can be also thought of as a point or a coordinate in a high-dimensional space. So for words, one common idea that works well is let's assign a number of parameters for each word, and then allow a neural network to actually learn what those parameter values should be. And this works really well. For many applications, we actually learn word representations that position the words into meaningful clusters. So words that are similar in some sense end up in similar areas of the vector space. And this is referred to as word embeddings, as we are embedding the words into a real value vector space. One problem with this is that we usually don't have too much, or we don't have enough training data for this kind of task. If we're training for a particular supervised task, then labeled data sets are normally quite small, and they won't contain all the words in all the possible combinations. Some of the words only occur 1 or 2 times. So we don't have enough data for learning good word representations. The solution to that is transfer learning. So we can learn good word representations on some other task or data set, and then transfer these over to our main task. And we can even use a task, the pre-training task could be something like an objective that doesn't require any manually annotated data. So that means we can just download huge amounts of data from the internet, plain text, and train our models on that. So this is what the famous continuous bag of words model does. It assumes that words that appear in similar contexts have a similar meaning. And it constructs a little neural network where it goes through text in sequence. It takes a particular word, then it takes the words around it, represents these as vectors, and then based on these vectors, it tries to learn, tries to predict what the target word in the middle is. And then it optimizes the whole thing, so it optimizes both the context vectors over here and the target vector over here. And we can train this on a huge amount of plain text and get really informative and useful word representations out of it. This is an example of what we get out. We have really nice clusters here of like kitchen, sink, bathroom, toilet in this area, and fan, light, and bulb in this area. So the words do end up in meaningful clusters based on how they're used in text. Just to note that these vectors are not usually just 2 or 3 dimensions long. This is just for visualization. Usually we use vectors that are 100 or 1,000 dimensions long, or even more these days. This is just an example of a real vector for the word bear that I took out of a model. And you can see there are 100 values here, all some small values around 0. We don't really know as humans what each of those values mean. It's an open area of research to actually interpret these vectors and the specific properties there. But we do know that this vector coordinate puts the word bear into an area of vector space that is similar to other words that have similar meaning. Now these vectors work really well. And they're really useful for many applications, but there's still a problem. And the problem is that the meaning of a word can depend on its context. So for example, here in these 2 sentences, I deposited some money in the bank, and I was camping on the east bank of the river. These 2 senses of the bank are clearly very different. If we use the same representation for both cases, our model is not going to work well. It's probably going to learn some kind of a mix between the 2 senses of the word. So it's probably going to suffer in both cases. And this is like an extreme case where these 2 words actually have very different senses, but in practice, the meaning of a word can change in more subtle ways when used in different contexts. So we definitely do want systems that, instead of pre-calculating a particular vector for a word, we want it to be able to dynamically calculate the vector representation for each word based on the context in which it appears. One way of doing that is to use recurrent neural networks. We can train an RNN to go through the text and predict the next word in the sequence based on the previous words. So here we have an RNN module that goes, oops, too fast, that goes through the text from left to right. At each step, it takes as input the current word and a vector representation of the context that it has encoded up to that point. It combines them together, and then it outputs two things. It outputs the prediction about the next word in the sequence, and it outputs a new vector representation of the context, which now includes the current word. And if we want to represent the word brown, including its context on the left, for example, then we can take this vector over here, and it has encoded all the information from the quick brown, and we can use it for some downstream application. If we want to encode the whole text, we just go through the whole text and take this final vector from here, and this now encodes the quick brown fox. Sorry. Yeah, go ahead.
How can we know how much this, let's say, H3 is capturing word meaning or kind of the representation of the word brown, and how much is actually the whole text before it?
Yeah, we don't really know. It's going to depend on the training objective, exactly how we train it. Also, if we're fine-tuning it for a particular end task, then it's going to learn to focus more or less to the context. But it's basically, at least it gives the model the ability to look at all the previous context. And well, the idea is that prediction of the next word in the sentence is a difficult enough task that you can't just do it based on the previous word. You do have to look at the words that come before it as well. So in most cases, the model is forced to look at more context and encode at least some information in the vector. But yeah, it's an interesting question. I mean, there's definitely work that has shown that RNNs forget information over time just because of the technical limitations. But it would be interesting to investigate, like, if they choose to forget some things and only focus on the very recent words, for example. So this idea is something that's used by a model called ELMO, which stands for Embeddings from Language Models. And what they do is they train two different RNN models, one going through the text left to right. So it tries to predict the next word in the sequence based on all the previous words. And then a second one going through the text right to left, trying to predict the previous word based on all the next words. And then we can just combine these together. So if we want to encode the word brown, given all of its context, then we can encode the quick brown with one language model, brown fox with the other language model, and then take the corresponding vectors, concatenate them together, and now we have this one vector that represents the word brown. It's focused on the word brown because it's the last word in both of these language models, but it has seen the entire context on both sides of that target word. So this is how ELMO works as a language encoder. In practice, it's a bit more complicated. They have two layers of bidirectional RNNs, and they take vectors from different points in that model. So they take a vector from the input, they take a vector after the first set of bidirectional RNNs, and a vector after the second set of bidirectional RNNs, and then combine these together. And the idea is that some tasks benefit more from lower level representations, other tasks benefit more from higher level representations. And by combining them together, we can give the model all the information we have, and then it can choose which type of information to use. This works quite well, and it can be combined with most NLP applications, most neural network models, or even many other types of models that are not neural networks. For example, if we have any kind of neural network for an NLP task, it probably uses some word representations. So now we can just concatenate a vector from Elmo to each of those representations, and the model probably starts working better just because now it has contextual word representations that have been pre-trained on some other data set. So that's a quick tour of the background. Now let's go to the state-of-the-art way of doing this, or the modern way of doing this. After Elmo was published, Google went ahead and published BERT. So this stands for Bidirectional Encoder Representations from Transformers, and it's also a play on words because Bert and Elmo are two Muppets from Sesame Street. It takes ideas from Elmo, it takes ideas from a few other papers, it puts them all together, and it scales it up more than it had ever been done before up to that point. And what it does is it takes a sequence of words as input, then it has a bunch of these transformer encoder blocks, and it gives as output a vector for each word that was given as input. And each of these vectors are now contextual representations for that word. So let's take a bit of a look inside as well to see how it works. So if we zoom into one of these green blocks, we have 3 green blocks here of the transformer blocks. Normally in full models it's more like 8 or 12 layers or even more. But if we zoom in, we see something like this. So we have vector representations of words going in, vector representations of the same number of words coming out, and then some operations in between. And we have 2 main operations. One is self-attention, and we'll talk about that in a moment. And then the other is feed-forward neural network, which just transforms the output of self-attention into a new vector space. So this is just a normal neural network layer. So what's happening inside self-attention? I'm not going to go into the full math equations. You can look them up in the paper if you want, but I'll just go over the main idea. The idea is that we calculate new representations for each of the words based on the previous representations of all the other words in the input. And the model is able to dynamically choose which words in the input are more important or less important for calculating the representation for one particular word. So here we have a visualization where we're calculating the vector for the word making, and the model has decided that the most important words here are more and difficult and making itself. So the previous representation of the word contributes a lot to the new representation, but in addition to that, it includes some information from surrounding words as well to get a more informative context-dependent representation. And here's another example. Here we're calculating a vector for the word it's, and the model doesn't actually look at the word it's at all, because the word it's doesn't really have a lot of meaning on its own. It prefers to look at the words in the context that this word is referring to. And this is a really good type of model, because now every word in the input is only one step away from every other word, as opposed to RNNs or LSTMs that came before it. We had to go through the text in sequence. So in order to get to the next word, we had to process the previous word. And if the next word depended on a word that came 10 words before it, then we had to do 10 different jumps in order to actually get to it. And we might actually forget some of the information from the original word before we get to it. In practice, we do this self-attention multiple times in parallel. So instead of just doing it once, we have multiple copies of self-attention, and this is called multi-head self-attention. And the idea is that each head learns to focus on a different aspect of the input. So maybe one head learns to focus on who did something. If we're trying to capture information about a verb, then maybe we're looking for, one head is looking for the subject, one head is looking for the object, etc. Again, because this is a neural network, it's kind of hard to interpret for sure and say that there are specific roles for a particular head, but the idea is that each head is able to learn to do something completely different from the others, and by having multiple copies of them, we're basically sending out little workers that analyze the input, combine input representations, and then construct vectors based on that, and then we just concatenate all of these vectors together to get a representation that captures the whole text from several different angles. So, question?
So
we got her.
So just could you elaborate a little bit on how this learning is done? You say every head is basically learning another aspect, let's say, who is doing what is done, and so on. But how is this learning done? Is there any sort of supervision coming into play, and how?
In a regular transformer model, no. We just construct these different heads and we initialize them randomly, so they start from different random places. And when we're optimizing them to do a task, because they have a different random initialization, they will end up in different places. And they learn their tasks automatically, basically. They learn to complement each other. They learn whatever they need to in order to solve the task well. At the end of the talk, actually, I'll talk about some of the experiments with my students where we do explicitly supervise the attention as well. But in regular models, this isn't done.
So the learning is completely unsupervised at this place, at this point?
At the head level, yes. So the heads are left to their own devices to figure out what they need to do. Overall, the model can be unsupervised in the sense of we can train it on unlabeled data, or it can be supervised if we train it for a particular supervised task.
Okay, thanks.
So we looked at the transformer component. So this module we just stack on top of each other. So you saw the 3 green blocks before. We just put 3 of those or 8 of those in sequence, and the model learns to transform the information in each layer. So the transformer component just takes a sequence of word vectors as input, and it outputs a new sequence of word vectors that have been transformed into something more useful. Yeah?
Would you mind elaborate a little bit on the computational intensivity of these models? I mean, it's my first time touching this topic, and I'm curious, one of the main objective of this topic can be implementing it on, I don't know, for instance, mobile applications, and how does it fit? I mean, when you're inferencing these models?
I'm not sure I caught everything. I understand the question is about computational complexity.
Yeah, and how can we implement, I mean, how big are these modules to be implemented on the hardware?
I mean, these are quite big models these days, and there is a lot of computation involved. So the self-attention component, for example, is n squared complexity in terms of the input, or the number of words that go as input, because for every word, we calculate its combination with every other word. So it is n squared, so there's a limit to how long sequences we can reasonably work with. There are extension models that extend this further and make it a bit more efficient. In practice, so transformer models, they're really designed for being deployed on parallel computation systems like GPUs. So that's why we use GPUs a lot, because they have a lot of different cores, and this computation can be parallelized there. And previously with RNNs, the computation happened in sequence through text. So in order to calculate the representation for each word, we had to calculate the representation before it. Here, with self-attention, the advantage is that we can calculate new representations for every word in parallel. So all of these operations can be parallelized to different threads or different GPU cores, and then they come back with all these informative vectors. So they're really well tuned and designed for parallelization, which makes them quite effective and efficient. So let's take a look at what's happening at the input before the words get to the transformer components. So here, one interesting property of the transformer is that by itself, it doesn't have any sense of order. Because everything is just one step away, everything is equal distance. So it doesn't matter if we give the model dog bites man or man bites dog, it would calculate exactly the same thing because it contains the same words. So we need to somehow handle this fact, because in language, it does matter in which order the words appear. So basically, we kind of do a hack in order to tell the model in which order the words appear, and we use position embeddings for that. So before the model starts computing with the transformer components, the inputs are just regular word embeddings, the old style embeddings where each token has its own vector representation. So these are the yellow ones over here. But we extend these by adding in segment embeddings. So these are vectors that represent which sentence a particular word came from. So this is useful for tasks where we have multiple sentences going in as input. And then we have position embeddings, where that just indicate the position in which the word appeared. So it's one embedding for the position 0, one embedding for position 1, one for position 2. And in the basic model, we're just adding these together and letting the model learn how to handle this addition operation, basically. We give the model this information, and it figures out on its own how to best use the information, basically. So how do we actually train this model? We want to train the model so that it learns general natural language information. We want it to learn more than one particular task. We want it to learn good word representations. We want it to learn how to combine those words together and how to construct meaning for a particular sentence. For that, we want to train it on as much data as possible. So one really nice training objective we can use is masked language modeling, because it requires no labeled data. And the idea is that we take the input text during our training, we select some percentage of the word in input, we replace those with the word mask, and then we just optimize the model to predict what the word behind that mask was. And this incentivizes the model to use all the available context information. It needs to look at the words that are available. It needs to learn how these words fit together, how to compose their semantics, and then figure out how to predict a word in the masked slot. So it's quite a difficult task, and by training our model to do this, the model learns really good vector representations for words, but it also learns how to combine those together into contextual representations. In practice, it's a bit more complicated, and it's like a fine balancing act in order to get it right. So if we do too little masking, then the training is very inefficient and takes a long time. If we do too much masking, then we're kind of hiding the content for our task, and it doesn't have any information to make predictions based on. So the actual strategy that's used in BERT is to pick 15% of the input words. Then 80% of those are replaced with a mask token, 10% are replaced with a random word, and 10% are left as the original word. And this might seem like a strange strategy, but the idea is that if we just masked everything that we select, all those 15%, then there's no guarantee that the model will actually learn good vector representations for words that are not masked. Because during training, it only needs vector representations for words that are masked. That's where the training objective is located. So it might not actually start doing constructing contextual representations for all the words. And in contrast, when we are actually using these models, we never mask our input, basically. We only want vector representations for words that are unmasked. In practice, BERT also included a second objective called next sentence prediction. And there the idea was, let's give 2 sentences input to BERT and have it predict whether the 2 sentences came in that particular order in the original data. In practice, later work has found that this task doesn't really provide much additional benefit, and most of the future encoders have actually omitted that. So the heavy lifting is done by the masked language modeling objective. Okay, so next, let's see how to actually use these models. So BERT-like models, oh, yeah?
A bit about the representations. So you mentioned that there would be something like 8 or 12 of those layers of these self-attention modules. Has it been looked into whether there is kind of the encoding eventually is lossy or not? So is there actually information lost as well? Or is it afterwards from the final representation possible to, in principle, reconstruct the original sentence exactly?
So I think these are two different questions. So with the lossy, you mean whether there's information in the lower layers that are then not captured in the upper layers?
Perhaps, yes, yeah. Or whether there is information in the original text that is not present in the highest layer at the end.
Yeah, so that's an interesting question. I'm not familiar with any good ways of actually measuring that.
Try to try to predict what the original sentence was from the final representation, and check whether you can easily build a model to do this reverse operation or not.
So that's kind of what the masked language modeling objective is doing, right? Because you're giving it a sentence and asking it to predict certain words. If you give it the full sentence as input without any masking, then it's a very easy task. It's just going to copy the input to the output. So it's a bit tricky. There is some work to show that some tasks benefit more from lower level representations than higher level ones. Similar to how Elmo used representations from different stages in the architecture. But I would say it's not commonly used. The direction at the moment is still bigger is better, so we would use the full model for different applications.
When training with masking objective, is the final word for that masked location predicted only from the final representation and not the lower layers?
Yeah.
Okay, so that suggests indeed that the final layer also needs to kind of keep all the information that is needed to reconstruct.
Yeah,
inputs.
exactly. So at least it has all the information for that task. It might be that the lower layers are doing some operations for extracting some information that then helps calculate the features for the higher layers, and that explicit information is then later omitted. But yeah, it's difficult to measure exactly with neural networks.
But that kind of also justifies the name transformer. So information is transformed and not, for example, deleted.
Yeah, exactly.
It is kept still. Yeah.
So let's see how to actually use these models in practice. So with BERT-like models, there are many models out there similar to BERT nowadays. They give us a vector representation for every input token, and we just have to, the normal practice is to just chop off the output layer, and this gives us the vector for that particular word. And we can use those word vectors to represent either individual tokens or full sentences. And there are two options, two strategies. We can either freeze the BERT model when we want vectors for a sentence. We give it some input, we calculate the vectors, then we take the vectors, put them into some other machine learning model and train the model to use those vectors. Or option two, which is more common these days, is to just put a small neural network on top of BERT and train the whole thing end to end. And this is called fine tuning. Now we're optimizing both the task-specific component and the full BERT model itself for one particular task. And that usually works better than option one. It now takes BERT, which has been pre-trained for some particular, to have like general good language representations, and then fine-tunes it for one particular task. And it works quite well. So if we want to do sentence classification, we just give an additional token as input. So this CLS token is here, along with the sentence that we want to classify. And we put an output layer on top of this CLS token representation at the output. And we train it to predict the class label. If we want to do token labeling, we put output layers on top of each of the token representations and train it to predict whatever tokens we wanted to predict. So this could be named entity recognition, it could be part of speech tagging, could be grammatical error detection. We can also work with tasks that have multiple sentences. So for example, natural language inference or entailment detection. There we give multiple sentences as input. We just separate those with a token, with a SEP token, and we use the positional embeddings to indicate which sentence contains which words. And then we put a classifier on top of this CLS token and train the model to predict a label for a sentence pair. Yes, question up there.
The transformers are limited in the window size they can get, right? So in your experience, if you have many sentences or multiple sentences, not just two, should we make the window bigger or should we just encode smaller pieces and combine them in some other way?
Yeah, it's a challenging question. Depends on the task and the data set. So these main models like BERT and Roberta, they're limited to 512 tokens of input. That is quite a lot. So for many applications, like if you want to encode 2 or 3 sentences, that's more than enough. If you're working with longer text than that, it can get difficult. There are special models designed for handling longer input. It's also quite common to just truncate the input, basically. So you slice off the end and ignore it. It's not ideal, but it's a technical limitation, basically. We can also do question answering. So here we need to give even longer input, but we can still do it for most applications. We give the question itself as input and a paragraph that contains that potentially contains the answer, and then we train the model to predict token level labels to indicate where in the text the answer is located. We can also do text generation. So, for example, if we want to transform text from one language to another, then we use an encoder to encode the text in one language. We can get a vector representation or a sequence of vectors out of it, and then we use a decoder model to decode this vector into a different language. And Mark is going to talk about that in more detail after lunch, and you'll see exactly how decoder models work and how we can use them for different language generation tasks. And this works really well. We can get convincing performance improvements on pretty much every natural language processing task by using these types of models. So here's just the results table from the original BERT paper, where each column is a different data set. They report the previous state-of-the-art results, and by including the BERT model into the architecture, they showed convincing and large improvements on all of the benchmarks. These types of models have now become very common. It's gotten to the point where it's difficult to find any NLP application that doesn't use a pre-trained transformer model. So they just give so much of a performance improvement that if you want to get competitive results, it doesn't make sense to not use it. Since BERT, there have been many spin-offs, many extensions, many improvements. So BERT was the original pre-trained transformer language model. After that, fairly soon, Facebook released Roberta. So Roberta got rid of the next sentence prediction objective. It optimized some of the hyperparameters. It was trained on much more data than BERT, and it outperformed BERT. Then after that, Microsoft released dBERTA, which specifically focused on better handling of the positional representations. It was trained on much more data than Roberta, and it outperformed Roberta. And this kind of competition between different companies just has been going ever since. Yeah, sure.
Use microphone. Use
Oh.
microphone. So is the reason the model outperforms so that they have actually more data, or that there is actually something inside the model which is better? What is the actual reason?
I mean, why we use more data for training and why that improves them?
No, I'm asking, you have 3 models, and
yeah.
The only difference there is that they tweaked something there and they used more data. Which part was the had more impact?
That's a good question. It's difficult to say. I don't remember if they did proper ablation experiments for Roberta and dBERTA, really. I agree, they should do that. Otherwise, you might end up in a situation where just you make an improvement in architecture that doesn't change anything, and then you train on more data and you get a better result. With these improvements, it did seem fairly convincing that they are sensible improvements. I do believe with Roberta, they showed the results both with next sentence prediction and without, and they showed that like it makes sense to just remove it. It's more efficient and it doesn't reduce performance. So they do make justified decisions, but a big part of the heavy lifting is indeed done by just training on more data, I have to say. I mean, it's similar to RNNs. So RNNs aren't really used these days, but part of that is down to the fact that it's difficult to train RNNs on as much data as these models are being trained on, because RNNs aren't optimized for parallelization as well as these models are. There's different models for different occasions as well. There's Alberta and DistillBERT if we want smaller versions of BERT, because BERT is quite large. Modern phones probably can handle it on the phone as well, but if we want it to be really fast and an environment where we can't use a whole lot of parameters, then Alberta and DistillBERT are the options. Big BERT and Longformer are for occasions where we want to handle very long text. Clinical BERT, MedBERT, different kinds of variations for applications where we want it to work on medical text specifically, for example. And there are different models for different domains. There are different models for different languages. German BERT, Camembert for French, EstBERT, which has been trained in Tartu. There's MBERT that was trained jointly on 104 different languages, and it should have some cross-lingual capabilities as well. So there's pretty much a BERT for every occasion. There are also multimodal models. So we can take data that has parallel images and text, and we can give some of the visual information as input to the transformer. So basically to the transformer, it looks like these are tokens, but they're actually segments from the image, and then train a full transformer model in a very similar way, doing next sentence prediction or masked language modeling to train it. And then we can use it for applications like visual question answering, for example. There's a repository called Hugging Face that contains a lot of these models. That's really convenient to use. And currently it has over 40,000 versions, different pre-trained transformers that you can download. Most of these are probably used by just one person, but the most well-known ones are really popular, really widely used, and if you need a pre-trained transformer for a particular occasion, it's worth looking into that repository to see if there's one that matches your application. Also, I wanted to give you an opportunity to try this out yourself. So I'm not going to run this live, but I made a Jupyter notebook at this URL that shows how to run a BERT text classification model. It has about 150 lines of code, and in those 150 lines, it does everything it needs. It sets up the environment, it downloads the data set, it downloads the pre-trained model, it fine-tunes the model, and it evaluates the model and prints some example output as well. It's commented as well, so if you want to play around with BERT or text classification, I suggest that's a good option to start. There's also a link, if you go to the Jupyter Notebook on GitHub, there's a blue button that takes you to Colab, and in Colab you can actually run that same code in browser on a Google server. And if you're logged in to Google and you change something from the settings to activate GPUs, then you can actually run this for free on a GPU on a Google server as well. So this particular code, it trains for sentiment detection. So it learns to classify sentences as either positive or negative sentiment. Okay, and now I'll tell you a bit about some of the interesting experiments that my students have done using these models. So one open area of investigation is how do these models actually learn, and what do they learn during the training process? Because these are neural network models and they're fairly new, there are still many open questions, and we just know that they perform really well, but oftentimes we don't know why or how. So in this set of experiments, we investigated specifically when do these encoder models learn general purpose patterns versus when do they learn individual data points. So what we did was we took training data for named entity recognition. We added a certain amount of label noise to this data, and then we evaluated the model. We trained the model on this noisy data, and we evaluated it on clean data. So here you can see the results. On the x-axis, we have the number of epochs. On the y-axis, we have performance. The red lines are performance of the training data. Blue lines are performance of the development data. And darker lines indicate models trained on training data with more noise. And we had a few different findings on these experiments. So finding one was that with these models, training separated into 3 different stages. So there's this first stage of general learning, where the model just learns general patterns and gets better both on the training set and on the development set. Then there's the second stage, which is basically a plateau. So there's not much change either in the training performance or on the development performance. And then there's a third stage of overfitting, where the model starts memorizing the noisy data points. Training performance goes up and development performance goes down. And this is very similar to previous generation neural network models in that there's a learning stage where performance goes up and an overfitting stage where performance goes down. But this kind of plateau stage is something new and a bit unusual, because previously it was taken for granted that performance just keeps on improving until the model starts overfitting. So here we see that these models actually have a fairly clear separation between when do they learn general patterns and when do they learn individual data points. And there's a margin of several epochs between those in the training process. Our finding number 2 was that the model is quite robust to noise. You can see that all of these blue lines are very close together. So the development set performance doesn't actually suffer much when trained on noisy data. Only one model with 50% label noise gets slightly lower performance on the development set. Everything else is very close together. So the model is quite robust to having noise in the training set. Oh, sorry, yeah.
These transformer-based models are typically sensitive to learning rate and temperature and schedulers and so on. So I mean, it takes a long time to get them to give the best performance. So how can you make such a comparison across different levels where different hyperparameters might be necessary and so on? Or what's the learning rate schedule or no schedule here?
So I believe we used standard learning rates and schedulers. So with these pre-trained models, it's...
standard doesn't exist.
With BERT, it kind of does. So with something like... we're using Adam as the optimization strategy, and that kind of handles dynamic learning rates. So tuning specific learning rates is much less common these days. I would say for each model, there's a particular learning rate that was tuned by the original paper and is then commonly used. It's possible that tuning specific learning rates for each of these noise variants would give slightly different results. We didn't try that, but yeah, I mean, that's true for any experiment, and there are way more hyperparameters than is possible to try. So we went for the general case, basically.
So this is fixed learning rate across all epochs, or?
The learning rate is fixed there. I don't remember off the top of my head if there was a learning schedule. There may have been.
Because then, I mean, you would force the system not to change anymore if the learning rate goes down, right? And then,
sorry?
I mean, if you have a decreasing learning rate, you more or less force the model not to change anymore, right? So then interpreting such curves is hard. But since they do change, probably it wasn't.
Yeah, exactly. I mean, we're using the same learning rate and the same schedule for all of them, so the differences are only due to noisy data points in the data.
So I have another question.
Yeah.
The nature of noise.
Oh, microphone. Right?
Sorry, the nature of noise. Does it is the noise really a random noise, or it can handle actually a systematic noise? Meaning that if I do a semi-automatic mislabeling, labeling of data, does it actually kind of recover from that? Or
so yeah, in this case, we focused on random noise. So just randomly permuting the labels on a percentage of the input. I do agree that if it's like structured noise, as in like some labels are more likely to be confused by others, then the effects might be different.
May I ask just a fundamental question? How did you end up with this direction of research? I mean, is it necessary to study the noise impact on this network? Is there any specific need for that? For some other applications, it makes sense, but is there any criticality here for this study?
It's to study how the models work, really. In a couple of slides, you'll see some of the applications that we came to using this research. Okay, I'll go on. So the third finding for us was that early stopping at a specific point with these models is less important than before. So it used to be that we would regularly evaluate our models on the development set and try to find the very best point for stopping. This result indicates that as long as we're stopping somewhere in the second stage, it's not as important anymore because we're getting very similar performance. And if the data is actually clean, then you can see that the line for the clean data set remains horizontal for most of the time. So again, there's not much threat of overtraining as long as the data set is clean. So nowadays, it is quite common to not do early stopping using a development set, but to just pick a particular number of epochs. And this graph kind of illustrates why that works and why it's not necessary to pick a particular point anymore. So these results showed that that learning of the general patterns gets separated from learning of specific data points. And we wanted to see if that allows us to actually identify which are the noisy data points. So we trained our model for a number of epochs, for 4 epochs in this case. And we then we measure the losses of all the training examples, and then we assume that these losses form 2 different clusters. So the cluster of high losses would be noisy data points, and the cluster of low losses would be clean data points. And then the task is to just find a threshold between 2 clusters in the data set. And here's a visualization of the histogram for our experiments. The blue lines indicate clean data points. The red lines indicate noisy data points. And you can see that they get separated quite nicely by the model itself. There is a little bit of red over here, there's a little bit of blue over here, but mostly there's a clear separation with a large margin in between. So if we put the threshold between them, we can use that for automatic classification. And we found that we can actually quite reliably predict if a label in the training set was noisy or not. If the noise is 50%, then we can actually identify with 97.9% F1 score whether a data point in the training set was noisy or not. So the model is basically learning the general purpose patterns first, and then this random noise kind of stands out in terms of loss. See if I have time. Not much. Just really quickly, another interesting direction of research that we did was interpretability of these models. So can we get the models to point to specific evidence in the input that leads it to make a particular prediction? And we formulated that as a task of zero-shot labeling. So given that the sentences are labeled, can we get the model to make predictions about individual tokens? So in this case, the task is grammatical error detection. Can we get the model, can we train the model for classifying sentences, but have it make predictions about which words in the input are grammatically correct and which ones are incorrect? And turns out we can do this. We can put self-attention network on top of the transformer model. And with a few modifications, we can make it into a token classifier. So one modification is that regular self-attention uses softmax, but softmax is really designed for picking one object in the input, whereas we wanted to be able to focus on many tokens in the input. So instead we used sigmoid. So now the task is kind of like a binary classification task for each token. And then we normalize those as, we normalize them using just a regular sum of all the weights. So now we can use these weights as the weights in a weighted sum for self-attention, and internally the model starts making binary predictions about each token. We also added a couple of losses that incentivize this further. So one loss tells the model that only some, but not all tokens in the sentence can have a positive label. So the model, so we don't basically want the model to go, oh, this is a positive sentence. Every word in this sentence is important and should be focused on. Some of those words should have no attention as well. And the second objective, that there are positive tokens in a sentence only if the overall sentence is positive. So if the sentence is negative, we want attention to be 0 across all the words, and only if the sentence level label is positive, we want it to have some words that it's focusing on. This works quite well, particularly for a model that's not supervised on the token level at all. And we found that it does slightly improve the sentence level performance as well to use this architecture. And to finish off, some examples here. So if we have a model, here we trained 4 different models on 4 different data sets for uncertainty detection, for grammatical error detection, negative sentiment, and positive sentiment. And we fed the same sentence through all of these models to see what tokens do they identify as important. So uncertainty model correctly identifies would, if, and possible as the important tokens. Grammatical error detection correctly identifies that there's some error in the sentence, although it puts it on slightly the wrong word. It should be on your. It correctly identifies that there's no negative sentiment, and it identifies appreciate as a word with positive sentiment. In the sentence up here, it correctly finds that there's no uncertainty. It identifies definitely as a spelling error. And one error that it makes is that it identifies disappointing both as negative sentiment and positive sentiment. And that's because these are opposite sides of the same problem. And if the sentence contains some negative sentiment, then that's an indicator that there's no positive sentiment in the sentence. So the model still chooses to focus on it. So it's an open research question. How can we actually force these representations apart so the model starts to distinguish which is the positive sentiment evidence and which is the negative sentiment evidence? So I'll finish here. I have a couple more slides on how we can actually supervise this attention. But if you're interested, then come talk to me, or I can send you some papers on it. Thank you very much. Any questions still? Yeah.
I'd like to ask about the model comparisons. You showed your findings and you showed some BERT versions comparisons.
Mm-hmm.
I'd like to ask, like, what do you essentially measure there? Because you started with, we basically assign some random, not random, but some vectors of numbers. How do you really assess the model? I mean, if it returned 5, 7, 8, and the other version would return 10, 15, 11, which one is better?
You mean how do we evaluate these different models?
Yes, basically.
Basically, we evaluate them on downstream tasks. So we take these pre-trained models, we train them for different tasks, could be 10, 20 different tasks, and we compare their performance on each. And that tells us, is this now a better representation or not?
All right, thanks.
Yeah.
So you showed that you can detect noisy labels. I assume that was after training the model. Later you checked whether so these noisy labels were they included in the same training, and then later you figured out that these were actually noisy.
Yes, exactly. So we have to first train the model on the noisy dataset, and then we can identify the noisy data points, and then we could either potentially filter them out or send them for review and train a new model.
So that's my question now coming up, that like, is it worthwhile then later to train a new model discarding those labeled data? Is it eventually turning out that noisy labeled data were harmful, or maybe it wasn't eventually?
So that comes back to some of the earlier results that the model is surprisingly robust, right? So even trained on noisy data, performance didn't deteriorate much. So for these types of models, it makes a little bit of difference, but not a huge difference filtering them out. But it can still be useful for other applications to be able to clean a data set, I think.
But did you actually try filtering them out and retraining? Because maybe even if they were wrongly labeled, maybe just seeing the data points still affected the learning process. So can't know whether that can be
I
good or
think
bad.
we ran some quick experiments, but I think there's still more to investigate in that area. We were focusing on just trying to identify the data points there. Yeah.
So yeah, is there any way to analyze these embedding spaces mathematically? I mean, it all looks a little bit mysterious still, and a little bit like a black box. So what's going on? So yeah, how do these spaces look like mathematically? What is their topology? How is it actually possible to capture the semantics of language in a mathematical way? So are there mathematical tools, or are there attempts to analyze these embedding spaces mathematically?
It's definitely an open area of research, and there are many people working on it. As far as I know, less from a mathematical angle, more from a visualization angle and probing angle. So putting different artificial tasks on these models to check have they learned this particular property at a particular point in the network. But it's, to a large extent, it's still a kind of a mystery, and the models just learn useful features for a particular task that they're trained for, and it can be quite challenging to try to interpret them at the moment. So we're still working on it.
Okay, let's thank Marek again, all the speakers of the morning.
Thanks very much.